In this section, we're going to be going over the fundamental theorems of calculus. So there's actually two of these theorems, the fundamental theorem of calculus 1 and the fundamental theorem of calculus 2. And these theorems are going to establish a connection between differential calculus and integrals. Okay, and then we're going to need to remember how to find the antiderivative functions from a given function, and that's going to help us determine the integral of a function. And we're also going to be using this in the next section as well. Okay, so starting with the fundamental theorem of calculus 1. The fundamental theorem of calculus 1, which we can denote as FTC1, is going to deal with functions that are defined like this equation right here. So g of x equals the integral from a to x of f of t dt, where f is continuous on that interval. Okay, so what does this actually mean? Well, if f of x, or if f of t rather, is positive on that whole entire interval, then g of x here can be interpreted as the area under the graph of f from a to x. And the x can vary from a to b. So what this actually is I recommend thinking about that function g of x as a cumulative area function. So cumulative area function meaning it's the area from the left all the way to some value x on the interval a to b. So this little graph right here is a pretty good representation of what we're actually doing. We can see that we have this function, this curve f of t, and g of x, which is the integral from a to x of f of t dt, is going to be the area underneath the curve from a to x. So for some of these questions, we're going to be asked to find g of b, where b is going to be some number. So what we're going to have to do is calculate the area under the curve of f from a to b. So that would be this whole entire area from a to b, and then this upper bound would be b if we're trying to find g of b. Okay, so let's go ahead and see an example here. If f is the function whose graph is shown below, and we know that g of x equals the integral from 0 to x of f of t dt, we want to find these values, g of 0, g of 1, g of 2, g of 3, g of 4, and g of 5. So since we have a function in this form, g of x equals the integral from 0 to x, so notice our a here is 0. That's kind of our starting point from 0 to x of f of t dt. Since it's in this form, we know that this is going to be using the fundamental theorem of calculus 1. And let's go ahead and start with g of 0. So let's find g of 0. So let's go ahead and write it like this. G of 0. Let's write it using this right here. It's going to be the integral from 0 to 0. So the x becomes a 0. And this is of f of t dt. So for this one, this is actually the easiest one that we have, because if you remember, if the bounds are the same, 0 to 0, then the answer is always going to be 0. So nice and simple for that one, we get g of 0 equals 0. So let's think about what this actually means. So what we're trying to do is we're finding the area underneath the curve from 0 to 0. Well, there's obviously no area there because the interval didn't move, so the area under the curve is 0. Next one, let's take a look at g of 1. G of 1, let's do the same thing and write it as the integral from 0 to 1 this time of f of t dt. Okay, for this one, we have to actually think about what this means. So we have to remember that we're trying to find the area underneath the curve. So we're trying to find the area underneath the curve from 0 to 1. Well, we just created a triangle, right? We just created a triangle here from 0 to 1. So we can actually use our geometric area formula for the area of a triangle to figure that out. We know that the area of a triangle is 1/2 base times height. That's 1/2. The base here is 1. The height is 2. So 1/2 base times height, which is 1/2 times 2, which gives us 1. So that gives us g of 1 is going to equal 1. And once again, this represents the area under the curve from the starting point of 0 to 1. Next one, let's take a look at g of 2. So g of 2, using the same initial setup here, it's going to be the integral from 0 to 2, f of t dt. And now we're going to be looking for the area under the curve from 0 to 2. So from 0 to 2, that's going to be from 0 to 2, so that's going to be this whole entire area right here. Well, what we can actually do here is use our geometric area formulas once again. We can split this up and say, well, that's going to be the area from 0 to 1 plus the area from 1 to 2. Because if we do that, that's going to be the area of a triangle, which we just did, plus the area of a rectangle. So let's go ahead and set it up like that. And let's set it up, let's rewrite the integral here. The integral from 0 to 2 is the same as the integral from 0 to 1 plus the integral from 1 to 2. Right? That's just pretty much the reason why we just said, just splitting up the interval from 0 to 2 to 0 to 1 and then 1 to 2. So we already found this right here. That was the first part right there. That was 1. So that's 1 plus. Now we need the second part. We need the integral from 1 to 2. That's just going to be the area of this rectangle here. So we know the area of a rectangle is just base times height. So the base is 1. The height is 2. So that's going to be 2 times 1. So 2 times 1, or 1 times 2. And that gives us 1 plus 2, so 3. And that gives us g of 2 equals 3. And next one, let's take a look at g of 3. So hopefully this is getting a little bit repetitive here. We want the integral from 0 to 3, f of t dt. So without even looking at the graph, we should expect that what we're going to do is something similar to what we just did, and that is going to be split it up and do the integral from 0 to 2 plus the integral from 2 to 3. And the same reason as before is because we already calculated this right here, the integral from 0 to 2, which was g of 2, which is the answer that we just found right above, similar to what we did up here where we split it up like this, where the answer to this one was g of 1. So now all we have to do is say, okay, that's going to be g of 2, which is 3 from right above, 3 plus, now we need to figure out the integral from 2 to 3. So the integral from 2 to 3 here, this is where we're going to just kind of make an assumption here and pretend like the area is given to us because it's a little bit more difficult to find because the function is curved. So we're actually just going to make the assumption that this area from 2 to 3 is about 1.3. Okay, so once again, pretend that's just given to us here. So 1.3, that gives us an answer of 4.3 for g of 3. Okay, last two, we want g of 4, and then g of 5 after that. So g of 4 is going to be the integral from 0 to 4, f of t dt. And for the same reasons we've seen already, that's going to be the integral from 0 to 3. We're going to split this up, plus the integral from 3 to 4. And then we do this because we already know that this one is g of 3. It's the last one that we just evaluated. So all we have to do now is figure out what the integral from 3 to 4 is. Let's go ahead and just write this out though. G of 3 we just found was 4.3. So that's 4.3 plus, so the integral from 3 to 4. We go up and we look at the graph. This is going to be another one that we're going to approximate here, and it's just assume that's given to us because it's a curved region. And we're going to say that this area is also 1.3. So we're going to say that all of these curved regions, this one, and then this one separately, and then this one over here, these are all going to be an area of 1.3. There's a little bit of a trick though, something to worry about, is that this portion is below the x-axis. That means it's going to be negative. So that's the one thing we have to look out for. So instead of adding 1.3, we're going to be adding the negative 1.3, which is obviously just subtracting 1.3, which gives us a net area of 3. And I'm just going to write that below it. So 4.3 minus 1.3, so that gives us g of 4 equals 3. So remember, the integral actually tells us the net area underneath the curve, meaning it could actually be negative because the area under a curve is negative. Okay, last one, we have g of 5. G of 5 is going to be the integral from 0 to 5 f of t dt. And we're going to split that up and say that's going to be the integral from 0 to 4, which is what we just found, which is why we split it up like this. And then 4 to 5. And we just found this was g of 4. And we found that g of 4 was 3. So that's 3 plus, so now we just need this one, the area under the curve from 4 to 5. So the area under the curve from 4 to 5 is going to be this area right here. Once again, we're just assuming that that's given to us as 1.3. But since it's below the curve, it's negative. So it's going to be plus a negative 1.3, which gives us 1.7. So g of 5 is 1.7. Okay, so you can see here in all these graphs shown below the regions that we're looking for, and you can see that they're the cumulative areas for this function. Okay, so here is just the fundamental theorem of calculus. Once again, just kind of in this more formal definition here. Fundamental theorem of calculus says that f is continuous on a to b. Then we have a function g, which is g of x, equals the integral a to x of f of t dt. And that's exactly what we've already been doing. So let's go ahead and do another example, except this one we're going to do by hand here. And the way that we're going to do it by hand is going to be using this little trick right here. So given this equation, if we're trying to find g prime of x, g prime of x is going to equal f of x. So we have f of t. So what we're going to be doing is plugging in an x into the t's in f of t. Okay, so for this, let's go ahead and see this example. We want to find the derivative of g of x equals the integral from 0 to x of the square root of 1 plus t squared dt. Okay, so using that definition, I'll write it right up here. We know that g of x, or rather g prime of x, so the derivative of this whole thing, equals f of x. So we do have to just be a little bit careful for these. We have to verify that it's continuous over the interval. And this is how we should be writing it out. We should say, since the square root of 1 plus t squared is continuous, then the fundamental theorem of calculus 1 is going to give us our result. And the result is that g prime of x, we're going to just use that function, but instead of in a t, we're going to be replacing it with an x. So we're going from 0 to 0 to x. So the x is going in here. So it's the square root of 1 plus x squared. Okay, so it's as simple as that for that problem. Let's see another example here. We want to find d dx of the integral of 1 to x to the fourth of secant t dt. Okay, so we have to be careful because this upper bound is not an x. When that happens, we are going to need the chain rule. Notice how the lower bound is a 1, it's not a 0 here. That will not affect these types of questions. Okay, so what we're going to be doing here using the chain rule, well, the easy way to think about it is this is going to equal, we're going to start off the same. We're going to plug this, because we're trying to find the derivative, we're going to plug that upper bound into t, so it becomes secant of x to the fourth. So it's pretty similar to what we just did. The difference is now it's essentially like the derivative of the inside, right? For chain rule, it's the derivative of the outside, leave the inside alone, times the derivative of the inside. So we just did the derivative of the inside, which was the derivative of the integral, so it stays secant. We left the inside alone. Now we do the derivative of the inside, which is the derivative of that upper bound. So that's the one tricky thing when the upper bound is something different like that. So now this is going to be the derivative of x to the fourth is power rule. That's 4x cubed. So now we're done. Now it's simply 4x cubed times secant of x to the fourth. Okay, so just a little bit tricky for that one, but if you know the little trick that you have to do using chain rule, then it's not too bad. Okay, that brings us to the next fundamental theorem of calculus, the fundamental theorem of calculus 2, which we're going to denote FTC 2. So now what we're going to be doing is we're going to be evaluating definite integrals, and we're actually going to be getting some numbers out. And this is because now our bounds or our limits of integration are going to be numbers. So if we have a function f, it's continuous on an interval a to b, then this is the fundamental theorem of calculus 2. So we have the integral of f of x dx from a to b, so those are numbers this time. Then we're going to evaluate that by finding the antiderivative of little f, which is we're going to call big F. So big F is the antiderivative of little f. We're going to find the antiderivative, and then we're going to plug in the upper bound, plug in the lower bound, and subtract those values. Okay, so find the antiderivative of the function, plug in the upper bound, minus plug in the lower bound, and evaluate to get a number. Okay, let's go ahead and see some examples here. So let's evaluate the integral from 1 to 2 of x dx. And just a reminder, we need this dx here. This tells us what our independent variable is. It tells us we're integrating with respect to x. Okay, so we need to find the antiderivative of x. And if we remember how to find the antiderivative of something like this power function, the antiderivative is we have to add 1 to the exponent and then divide by that new exponent. So the antiderivative of x is 1/2 x squared, or x squared over 2. Okay, so anytime we just have a little power function like this, just a variable, then we add 1 to the exponent, divide by the new exponent. That's the antiderivative. Okay, so what we have here is the integral from 1 to 2, just rewriting what we have of x dx, is going to be 1/2 x squared evaluated from 1 to 2. So that's the notation we should be using. That vertical line means evaluated from x equals 1 to x equals 2. So that means we go ahead and plug it in. So it's going to be 1/2 upper bound minus the lower bound. So it's 1/2 2 squared minus 1/2 1 squared. So all we did was plug in upper bound minus lower bound. And now we can just go ahead and evaluate this. So we get 1/2 times 4, which is 2, minus 1/2 times 1, which is just 1/2. And that gives us a value of either 1.5 or 3/2. Okay, let's go ahead and draw out a graph of what we just did. So if we know what the graph of y equals x looks like, that would look something like this: straight line, slope of 1, y-intercept of 0. And from 1 to 2, that would be this region right here, this filled in shaded region from the curve down to the x-axis. So what we actually just found is that the area of that shaded region is 1.5 or 3/2. Okay, so let's go to the next one. We want to evaluate the integral from 0 to 1 of 2t cubed plus 4t plus 1. So we need to find the antiderivative of those three terms, and we can do them separately because they're separated by addition or subtraction. So taking a look at the first term, and then we'll do the second and then the third. So this is a power function here, 2t cubed. We're going to add 1 to the exponent, divide by that new exponent, so it becomes 2t to the 4th divided by 4, which is 1/2 t to the 4th. The next one is, let's take a look at 4t. So the antiderivative of 4t is going to be add 1 to the exponent, divide by that new exponent. The antiderivative is 2t squared. And then the last one, we have the antiderivative of 1. So if you remember, the antiderivative of 1 of a constant is just taking the constant and multiplying it by the variable. So that's 1 times t, which is just t. Another way to think about it, if you remember, 1 can be rewritten as 1 times t to the 0, because t to the 0 is equal to 1. So you can think about this as adding 1 to the exponent and then dividing by 1. So that would become t to the 1st divided by 1, which is just t. So obviously you don't have to think about it that way. If you have a constant, the antiderivative is just multiplying it by the variable. Okay, so let's go ahead and write this out here. So we just did the integral from 0 to 1 of 2t cubed plus 4t plus 1 dt. We just found that the antiderivative is 1/2 t to the 4th plus 2t squared plus t. And we're going to evaluate that from 0 to 1. So we're going to plug in the upper bound and then minus, and then plug in the lower bound and then evaluate. So let's plug in the upper bound first. So we have 1/2 1 to the 4th plus 2 times 1 squared plus 1. So that's upper bound minus lower bound. Now we plug in the lower bound here. Plugging in the lower bound is pretty easy, right? Because we're plugging in a 0 into everything. And in this case, when we do that, everything's just going to cancel off to 0, which is pretty nice. So let's go ahead and simplify. The first upper bound portion becomes 1/2 plus 2 plus 1 minus the whole second half portion is just 0. So 1/2 plus 2 plus 1 we would get common denominators. That's 1/2 plus 4/2 plus 2/2. That would end up being 1 plus 4 plus 2 is 7, 7/2. Okay, so this would be the, I don't know what the graph of this original function looks like off the top of my head, but it would represent either the positive area, depending if it's above the x-axis, or the net area, if it's above and below the x-axis. Okay, next one. Basically, let's have several more examples of this concept. Evaluate the integral from 1 to 3 of e to the x dx. So we should know that the antiderivative of e to the x is itself, e to the x, right? Because when you take the derivative of e to the x, you get e to the x. So that means the antiderivative is the same thing. So all we have to do here is say, well, this integral is going to equal the antiderivative evaluated from 1 to 3. So something, if you were reading the definition carefully for the fundamental theorem of calculus 2, you would see that it says any antiderivative. What we're doing is the most general antiderivative. Remember, if you do any antiderivative, technically we could do plus c. We could say, well, any antiderivative, one of them could be e to the x plus c. It could be e to the x plus 7 minus 1 million. If we did plus c and we carried out our calculations, you would see that that constant would actually cancel itself out. That's why when we actually do this, we just do the most basic version, which is not included with any plus constant. Okay, so all we have is e to the x from 3 to 1. So we plug in upper bound minus lower bound. So that's e cubed minus e to the first. And we're just going to leave it like that. E cubed minus e, whatever that number happens to be, we're going to leave it just like that. Okay, so typically, like I'm sure we mentioned at some point, if you have pi in your answer or e in your answer, you're just going to, or square root, that does not simplify nicely. You're just going to leave it as is for your final answer. Okay, next one we have evaluate the integral from 3 to 6 of dx over x. So we should know that this is the same thing as the integral from 3 to 6 of 1 over x dx, right? That's just a different way of rewriting that. So now we need to think, what's the antiderivative of 1 over x? We should be thinking, what do we take the derivative of and get 1 over x? The answer is the ln of x. And also remember, thinking back to antiderivatives, we need to have these absolute value bars because 1 over x can be negative. However, ln of x cannot be negative. X has to be positive, so we ensure that it's positive by putting absolute value bars around the x. So we just found that the integral from 3 to 6 of dx over x equals the ln of the absolute value of x evaluated from 3 to 6. We plug in upper bound minus lower bound. That's the ln of 6 minus the ln of 3. And we don't need the absolute value bars anymore because 6 and 3 are positive numbers, so we don't have to worry about that absolute value bar. They're already positive. And even though this is technically correct, this just represents some number. Let's recall some logarithmic properties. If you have the same logs and the same bases, and it's separated by addition or subtraction, you can combine them, addition or subtraction, you can combine them. Since this is subtraction, we can combine them using division. 6 divided by 3, which is 2. So we get the ln of 2. Okay, so that just represents a number, whatever the ln of 2 is, but we're just going to leave it just like that to make sure it's completely accurate. Okay, next one, we want to compute the area of the shaded region under the graph of f of x equals x cubed plus 2x plus 1 from x equals 0 to x equals 1. So what does that mean? That means we are doing the integral from 0 to 1 of this function, and that will tell us the area under the region. So let's take a look at this region. I already have it graphed out here. So here it is, the function f of x from 0 to 1. You can see this area is all positive. It's above the x-axis, so it's going to be an actual area under the graph, and we don't have to think about it as a net area. It's just the actual area. Okay, so let's go ahead and do this. So I'm going to skip ahead here and find the antiderivative of all three terms. The first term is going to be 1/4 x to the 4th. The second term is going to be x squared. The last term is going to be x. Okay, so hopefully you can do that on your own. Take a second maybe and think about how I did that. We're going to evaluate this from 0 to 1. So we're going to go ahead and plug in the upper bound and get 1/4 times 1 to the 4th plus 1 squared plus 1 minus plug in the lower bound. Notice that if you plug in 0 to all of these terms, it's going to cancel everything to 0. Be careful though, because plugging in a 0 to something does not automatically make it 0. So just make sure it is 0 before you say that it's 0. So now we go ahead and simplify this. This is 1/4 plus 1 plus 1. We get 1/4 plus 2. Getting common denominators, that would be 9/4 or 2.25. Okay, and then as we can see in our answer here on the graph, 2.25, it's the same as 9/4. Okay, next example. We want to compute the area of the shaded region under the graph of f of x equals cosine x from 0 to pi over 2. So let's think about this graph. The graph of cosine from 0 to pi over 2. So here's cosine from 0 to 2 pi. Here is pi over 2. So this is going to give us a nice positive area from 0 to pi over 2. And what we're going to have to do here is integrate from 0 to pi over 2 of our function cosine of x dx. So we think, what's the antiderivative of cosine? We should have these memorized already, but think to yourself, what do you take the derivative of to get cosine? And the answer to that is sine. So the antiderivative of cosine is sine. Evaluate this from 0 to pi over 2. All we have to do is plug in upper bound minus lower bound. So sine of pi over 2 is 1. Sine of 0 is 0. So 1 minus 0 gives us 1. So the area under the curve for cosine of x from 0 to pi over 2 is actually 1. Let's take a look at the graph again. So here's the graph of cosine of x, a little bit condensed from what I had drawn earlier, from 0 to pi over 2. So that curved cosine function actually ends up giving us a nice perfect area of 1 underneath the curve for that interval. Okay, last thing here, example, what is wrong with this calculation? We have the integral from -1 to 3 of 1 over x squared dx. So if we were trying to take the antiderivative of 1 over x squared, we could rewrite that as x to the -2. Taking the antiderivative, what we could say is, okay, let's add 1 and divide by that new exponent. That would give us x to the negative 1 over negative 1, which is written right here. And then we could plug in the upper bound of 3, and then get this, subtract, plug in the lower bound of negative 1, get this, and then evaluate and get negative 4/3. So everything seems fine, but there is something wrong with this. There's kind of two things that tells us why this is wrong. First, we should notice that, let's think about the first thing, maybe the graph. 1 over x squared looks something like this. So if we're going from negative 1 to positive 3, we can clearly see that this function is positive, right? It's above the x-axis the whole time. And if the function's positive on the interval, then that means the integral of the function on that interval should also be positive, which we got a negative answer. So that's one issue. That's how we know that there's something wrong here. The main issue is that this is not continuous. It's not continuous over the interval from 1 to 3. And that is because there is an infinite discontinuity at x equals 0. And an infinite discontinuity means there's a vertical asymptote there. And in order to actually evaluate an integral, a definite integral like this, it has to be continuous over that interval. We didn't have any issues because the examples that we did, I made sure that they were continuous, but you do have to watch out for that. And what happens when it's discontinuous is that we actually end up getting that the integral does not exist. Okay, so a little tricky. If it's discontinuous on the interval, then it actually does not exist for that integral. Okay, so we have our two things for this section, the fundamental theorem of calculus. The first one, and the second one, so make sure that you know both of them, and that is it for this section.